So welcome to this. This is the Further Math Support Program online revision session for OCR Statistics 2. And in this session we're going to look at hypothesis testing. Now hypothesis testing is quite critical in statistics. It's the experiment that you would do in statistics, and everything's pretty much been using towards this. Okay, so what's really important is that you understand how to be able to set up a hypothesis test correctly. Making sure that both your null and alternate hypotheses are correct, and that you then obviously are able to perform out the test correctly. You need to be able to do it with the Poisson distribution. Okay, you need to be able to do it with a normal distribution as long as you know what the variance is, and if you don't and you have a large sample, then we can use this thing called the central limit theorem and an unbiased estimator of sigma squared as your variance to do this. Also, you need to appreciate that there is error when you do hypothesis tests, and you are expected to be able to calculate those errors as well. So you need to know the difference between type 1 and type 2 errors, and as I say, also calculate them. So we've got a situation here. And again, I've truncated the table just to warn you here. So the random variable r has a binomial distribution. Okay, so you can be asked to use other distributions as well, not just the normal or Poisson, but this is about type 1 errors. So the null hypothesis. So when you do a hypothesis test, you need this thing called a null hypothesis, and you need an alternate hypothesis. Okay, so we've got a null hypothesis of 0.7 is to be tested against the alternate hypothesis h1 of p being less than 0.7. And we're doing this at something called a 5% significance level. And what we're asked to do is to work out the critical region for the test. So I'm just going to formalize this in a slightly different way. So p is equal to 0.7, h1 is p is less than 0.7. This makes it a one-tailed test. So in other words, I'm going to look at the bottom tail. So I'm looking for the probability of being less than or equal to a specific value. It's got to be less than or equal to the significance level. Okay, so what we do is we look in your table for a binomial of 10 and a p of 0.7, okay, for our critical value. And we can see that here the probability of r being less than or equal to 4 is in fact 0.0473. So this is done by looking it through a table. So you get 1 mark for doing this. So therefore we know that your critical value is equal to 4 excuse me, and your critical region is any value that is less than and equal to your critical value. Okay, so we're getting 2 marks for that. Now, type 1 error, you need to know this. So a type 1 error is the probability of rejecting h0 when in fact true. Okay, and actually it's exactly the same as the probability of the true significance. And that is the probability of being in your critical region. So the probability for type 1 error in this particular case is actually really quite pleasant, because it's just going to be 0.0473. So there are 3 marks awarded to this. You get 1 mark for looking it up correctly in the table, you get an accuracy mark for stating your critical region correctly, and then you get your final accuracy mark here for stating the significance level effectively. So this time in part 2 we are now given that p is a specific value. So I'm now told that r is a binomial distribution of 10, 0.4, and I want the probability of a type 2 error. Now a type 2 error is where you do not reject h0 when in fact you should have done. Okay, so this is the probability of not rejecting h0 when it was false. Okay, and the way of doing this in this particular case is it's the probability of being in the critical region or not being in the critical region, given that you actually have a binomial of 10, 0.4. Okay, so we need to work this through. So not the critical region, so this is the probability of not being in the critical region, given that your distribution really is this. Okay, and I know that because it's telling me that in the question. Okay, so just following this through, this is 1 minus the probability of x being less than and equal to 4, given that you're dealing with this binomial. So here's my 0.4 from this table. So this is 1 minus 0.6331, which is going to give me the grand answer of 0.3669. Okay, so another name for not the critical region is called the acceptance region. So this thing here is your acceptance region. Okay, and that enables you to work out this probability of a type 2 error. They are usually quite big, type 2 errors, just to warn you, so don't be too fazed by that. Okay, so how are your marks awarded here? Well, you get 1 mark for a combination of using the distribution correctly and using the acceptance region correctly. So that's a method 1 mark. So this step here is quite important. Okay, it tells you everything you want to know. You then get another mark for doing 1 minus that to turn it round so that you can use the tables, and then you get your final accuracy mark for the end question. So this is quite nice. Okay, so given that P is equally likely to take the values of 0.4 and 0.7, find the probability that the test in total results in a type 2 error. Well, you've got half the probability of being 0.7, you've got half the probability of being 0.4. Okay, so this is really quite nice. So you've got half the probability of making a type 2 error, really. So given that you're in the critical region, not in the critical region when you shouldn't be, that's only going to happen half of the time. So it's going to be 0.5 times by 0.3669, which is going to give me 0.18345. Okay, so you get a method mark for recognizing that because it's equally likely to be shared across the two values, we've got half the probability of making a type 2 error. You then get your accuracy mark for your final answer. Okay, so this is a typical question dealing with how we work out the probabilities of type 1 and type 2 errors. So, June 2011, question 6. Records show that before 1990, the maximum daily temperature at a seaside resort in August can be modelled by a distribution with mean 24.3. So we're not told what the distribution is. The maximum temperatures of 50 August days since 1990 can be summarised as below. And basically we've got to do a test. And it's worth a lot of marks. Okay, so that's just something we need to be very, very conscious of. So, because we've got a large sample size, 50 is regarded as a large sample size, we can actually use something called the central limit theorem to deal with the mean. Okay, so the central limit theorem states basically that as long as your sample size is large enough, it doesn't matter what your initial distribution is, the means can be modelled as a normal distribution of mu over sigma squared over n. And again, for a large sample, we can use sigma squared hat, okay, or s squared. You sometimes see that as an approximator. Okay, it's not really normally distributed, but as long as the sample size is large enough, then we can use this. Okay, so there's quite a lot of work that is required before we do this. I'd quite like to work out my distribution before I start to formalize my hypothesis test. Okay, just to make us aware of how that works. So I'd rather be quite keen to work out my test statistic. Now I'm going to let T be temperature, because that's what they've used here. So I can work out T bar. So T bar is going to be 1314.0 over 50, which works out to be 26.28. And I also want to work out sigma squared. Okay, but I'm doing an approximation of that. So there's lots of ways of doing this. I prefer to use STT over n minus 1. So STT is the sum of t squared minus the sum of t squared all over n, and then I'm going to divide that by 1 over n minus 1. Okay, if I see that formula, things are going quite nicely. So we're going to have 1 over 49, lots of 36602.17 minus 1314 squared over 50. Okay, and if we calculate that, that's going to give me a value of 42.25. Okay, so what this means is my mean distribution, I'm going to do this in a different color because it's quite important. My mean distribution, t bar, is actually going to be normally distributed, actually approximately normally distributed. We're not worried about that, but by the central limit theorem as being 24.3. Okay, now I can't really write that because I don't really know it yet. It's just what we thought it could be, so we like to keep that as mu for now. And sigma squared, we're going to use 42.25. Okay, what we can then do is set my hypothesis. So my null hypothesis is the belief that there has been a change. So what we do is we set your null hypothesis to say that there hasn't been a change, and my alternate hypothesis is that there is a change. So that means it's not equal to 24.3. So this tells me that I'm actually now dealing with a two-tailed test. That's really important to bear in mind. So it's two-tailed at 1%, which implies 0.5% in each tail. Okay, so we've actually got quite a lot of marks now. Okay, just by doing what we've just done there, we've now got 5 marks. Okay, you get a B mark for setting up this, a B mark for setting up your alternate hypothesis, you get a B mark for working out effectively what's your test statistic, and you get 2 method marks. Okay, there you are. Actually you get 6 marks. You get 2 method marks for calculating here and an accuracy mark as well. So you get 6 marks just for setting up and finding all your variables, which is quite nice. Now, to do this, we're going to have to do some standardization. Okay, so I know that my z value, because I'm dealing with a normal distribution, my z value is going to equal t bar minus my assumed mu over, in this case, sigma squared over n rooted. Okay, now you're given that in a formula sheet, so it's not so bad. So if we calculate this, it's going to give me 26.28 minus 24.3, all divided by the square root of 42.25 divided by 50. And that's going to give me my what we call test statistic, which is 2.154. Now, what we do in this particular test is we work out something called your critical value. And your critical value comes from the probability table that we've got. So we're dealing with a 0.5% because it's two-tailed distribution. That corresponds to this probability. So I know that my 2.576 is what we call your critical value. Okay, so just to show you where we're at this point here. Okay, we've now got another method mark for working out your test statistic. Okay, followed by your accuracy mark. You then get another accuracy mark for effectively finding your critical value. So what we now comment is that your test statistic is less than your critical value. This means you're not in the critical region, so therefore we do not reject H0. Okay, so that gives me a method mark, and you need to contextualize. So there is insufficient evidence. Always do this, please. There's insufficient evidence to suggest a change in maximum daily temperature. And my advice is you take that directly from the question. Okay, don't sort of try to interpret or anything. Literally just restate what you've got. So maximum daily temperature, and that's where you get your final accuracy mark. Okay, so these are not that bad, it's just quite long. Okay, but the normal distribution one pretty much follows this. There are other ways of doing this, but that in my view is the most usual way of doing it. Okay, and then it's asking us why we're able to use the central limit theorem. Okay, and I mentioned this earlier. The basic premise is that n is large. Large n allows you, because we don't know it's normally distributed, to approximate. Okay, so another question. We've got a temporary job is advertised annually. the number of applicants for the job is a random variable which is known from many years' experience to be a Poisson distribution. Okay? In 2010 there were 19 applicants for the job. Okay? Test at 10% whether there is evidence of an increase in the mean number of jobs for the applicants for the number of jobs. Okay, so we're going to set this up. So I have a belief that the rate is equal to 12. However, there is evidence to suggest that it may have increased. So that is how you would set up your hypotheses. Okay, I've got 2 marks now, which is quite nice. Okay, so that's fine. We just now need to set up the test. So there's lots of ways of doing this. I personally prefer to use critical values rather than test statistics, but I'm going to show you 2 ways of doing this. So first of all, your test statistic is greater than the mean. So therefore I'm going to be looking at the top end tail. That's a good indicator of how these work. So what you can do is you can work out the probability of being greater than or equal to your test statistic. Okay, now we know that that's 1 minus the probability of x being less than or equal to 18. Okay, and we can look that up in your table. Okay, so Poisson 12 being less than or equal to 18, so the probability of x being less than or equal to 18 is actually equal to 0.9626. Okay, so the probability of being greater than or equal to your mean is actually equal to 0.0374. Now this is less than 10%. Okay, so 0.0374 is less than your significance level, therefore we reject H0. Okay, and I'll conclude that in a minute once I've shown you the other way of doing this. So the other way is to find something called a critical region. Okay, now because we're dealing with the top end, we're looking for a value such that if we exceed it, we're in the top 5%. So turning the probabilities round, and you may want to just convince yourself that this statement is true. Whoops, sorry, 0.1 is 0.9. Okay, so you might want to convince yourself that that statement is true. So what we do is we look for the first probability that exceeds 0.9, which is this one here. So I know that the probability of x being less than or equal to 17 is equal to 0.9370. So therefore C2 minus 1 is 17, so C2 is equal to 18. Okay, so therefore your critical region is x being greater than or equal to 18. So as a consequence, your test statistic is a member of your critical region, so therefore we would reject H0. So there are 2 ways of getting to that point. Then of course we do need to finish it off and do your final conclusion. Okay, so we've rejected H0, we can say that, so there is sufficient evidence to suggest, that's always important to write these things, so there's sufficient evidence to suggest an increase, and again you fully apply this, so an increase in the mean number of applicants. Okay, so I've shown you 2 ways here of dealing with this particular hypothesis test. Okay, so learn both. It's quite useful. Sometimes one is quicker than the other. So that's everything about hypothesis testing really. So just make sure you're able to answer all of the exam questions on that, and then everything will be fine.